Hello, everyone. Welcome to session 8 of the Applied AI seminar series. Today, I'm going to be talking about Bayesian ML for healthcare applications. Let me give a brief introduction to Bayesian methods in healthcare. So the Bayesian approach incorporates prior knowledge and updates beliefs with new data. This is a very powerful probabilistic framework which handles uncertainties in medical data and predictions. It's extremely flexible as well. It adapts to various healthcare applications, diagnosis, prognosis, and treatment planning. It's also very interpretable in that it provides probability distributions, not just point estimates. You can have an uncertainty assigned to a unique prediction. So it's a very useful tool. It's also very scalable, so it's suitable for both small clinical studies and large-scale healthcare data analysis. Gaussian processes are extremely useful in healthcare. They're non-parametric, flexible models for regression and classification tasks. They utilize a kernel-based approach which captures complex patterns in medical data. They also employ uncertainty quantification, which provides confidence intervals for predictions, and they handle small data sets effectively. They're adaptable and can be used for many applications. GPyTorch is a deep neural net framework for implementing Bayesian methods. It's a way to implement Gaussian processes for modern machine learning systems. It's a very useful and scalable technique, which can be applied very simply. So if you are familiar with utilizing PyTorch, it's extremely easy to switch to utilizing GPyTorch for Gaussian process-based predictions. So it combines deep learning feature extraction with GP classification. In the example that I'm going to be talking about today, we utilize CLIP for efficient image feature extraction. We're utilizing a GP layer, which implements variational inference for scalable GP classification. We're utilizing a soft max likelihood for multi-class prediction, and we're utilizing a variational elbow and evidence-based lower bound as the objective function. And we're able to obtain uncertainties from these predictions and also obtain probabilities related to how likely the outcome is for certain data points. So I have a demo associated with this. Let me just go ahead and switch to that demo. This is running on our CHPC. This is utilizing a Gaussian process within the GPyTorch framework, and we're utilizing the CLIP embeddings with chest X-ray images. So this might look similar to some of the tutorials that I've given previously, but the main point is we have a bunch of chest X-rays that we're utilizing as our input data set, and they have a certain label of pneumonia versus non-pneumonia. We are generating CLIP embeddings. So we download the data set, initialize the model, and create a custom data loader to utilize this data. All of the images within that custom data loader are comprised of the CLIP embeddings. So we generate the CLIP embeddings utilizing the CLIP model, and we can then define our Gaussian process model. So we have a classification model where we're defining the variational distribution, the variational strategy, and we define this is a very simple model. We have a very simple training function. This is similar to any training function that you would see for any deep learning process. We have an evaluation code, which is basically an inference code. We can actually train this model on the CHPC. Here I'm utilizing an AtomW-based optimizer, and you can see the loss over each epoch. It's reducing, so it's learning something. And ultimately, we come out with the test accuracy of 74%. From there, we can create confusion matrices to visualize the outputs of the model and also visualize the distribution of prediction uncertainties. This is a starter code that is provided to everybody. It's in our RCIF Applied AI seminar series GitHub repo. So this code, which is available for anybody to get started working with Gaussian processes and image-based data. This is a free code to utilize. You can utilize it with your own data. I'm happy to sit down and discuss with anybody how to utilize it for tabular or image-based data, you can generate predictions with uncertainties within a deep learning framework. Some components of the Bayesian model are the prior, which incorporates domain knowledge about the problem. The likelihood models the data generation process. The posterior is the updated beliefs after observing the data. We have a marginal likelihood as well, which is used for model comparison and hyperparameter tuning. And we have a predictive distribution, which provides probabilistic predictions for new data points. Advantages of Gaussian processes and medical imaging are the fact that it comes with uncertainty quantification, which is critical for making reliable medical decisions. It's interpretable, so the radial basis function, kernel function, can be designed to reflect medical knowledge. This within the context of active learning, efficiently select most informative samples for labeling. If there's a lot of uncertainty around a certain region, we can go back and add more data or refine the training set to get better predictions. It's a very robust model which handles noise and outliers common in medical data. In terms of practical implementation with GPyTorch, it is integrated with PyTorch, so it leverages GPU acceleration and automatic differentiation. It's very scalable. It utilizes inducing points for large-scale data sets, supports custom mean and kernel functions, and it can handle multiple related medical tasks simultaneously. So you can have multitask learning where you have multiple input, multiple output. Model selection, there's tools for kernel and hyperparameter optimization within GPyTorch as well. Some of the limitations, though, are scalability. GPs are very computational complex, O n cubed in terms of computation and O n squared in terms of data storage. They're not necessarily the most scalable models, but there's certain tricks that can be applied to make them scalable. The approximation quality of GPs is susceptible to giving mispredictions in highly nonlinear or complex data. The hyperparameters are sensitive to the choice of kernels and hyperparameters, so poor selection can lead to overfitting or underfitting, and it requires careful tuning that can be computationally expensive. There's also the limitation of non-Gaussian noise. So Gaussian processes inherently assume Gaussian noise in the data. If you're dealing with non-Gaussian noise, it requires custom likelihood functions, which can be complex to implement and computationally expensive. Standard GPs also assume stationary in the data, which can be limiting when dealing with non-stationary processes. You can extend to non-stationary kernels, but it adds complexity. And even though they are interpretable, it can be complex when working in high dimensional spaces. In terms of evaluation and interpretability, some common tools that are used when working with Gaussian processes are confusion matrices, which can assess the model performance across different classes. Uncertainty visualization, you can make histograms of the prediction entropies. You can also create ROC and PR curves, which evaluate the model discrimination ability. And calibration plots are also a good way to ensure the reliability of the predicted probabilities. There's a lot of ways to evaluate the performance of Gaussian process-based methods, but it's a very powerful technique, which is useful for modeling complex data and having unique uncertainties associated with the data points, which is some of the challenges in future directions are data scarcity. Developing methods for learning from limited labeled data, the interpretability can be somewhat complex. The computational efficiency is somewhat difficult if you're scaling to larger data sets and utilizing this in inference because it is computationally expensive and memory expensive. Combining imaging with other clinical data sources can be complex as well, but it is possible. It's also very interesting to consider the idea of incorporating causal relationships within the Bayesian model. That is something that has limited publications on the topic, but it is possible. This can be used for adaptive personalized medicine. So you can have models which are personalized to individual patients. So it's potentially useful in that direction. In summary, Bayesian methods, particularly Gaussian processes, offer powerful tools for healthcare applications. GPyTorch provides a flexible framework for implementing GP models in medical imaging. The uncertainty quantification aspect of the tool is crucial for responsible AI in healthcare, and ongoing research can help address the issues of data scarcity and interpretability of these models. They do require a relatively large amount of data compared to other models, and they are a little bit more complex to train than a standard like CNN off the shelf, but they're very powerful. The future of Bayesian ML in healthcare promises more accurate, reliable, and personalized medical decision support systems. This is a very powerful technique, and it can provide a lot of value in terms of quantifying uncertainty and helping to refine training sets and helping to give the most accurate predictions with uncertainties for medical applications. I'm hopeful that the code that I'm going to be sharing with everybody will be useful, and I hope it'll be a good starting point for an introduction to Gaussian processes. And again, my name is Dennis Trujillo, and I'm happy to spend time to help anybody who's here get started on utilizing this code or utilizing it within our CHPC environment. We're a standalone compute center separate from RIS, and we have access to some really amazing compute. So we have access to some super powerful GPUs, and we'd love to get you running on them. I'll be sending out a follow-on email to everybody and providing more information there. If there's any questions from the audience, I'd be happy to take them.
Dennis, oh, you can hear me. Yeah, you mentioned some of these GP models are sensitive to tuning parameters. Is one of those tuning parameters the choice of the prior distribution? And is there like a typical prior that would be used in these models?
You can use a prior that's based on your own training set data. You can define a prior based on a subset of that, like a distribution of your training set that is assumed to be normally distributed. So you can create your own priors, or you can utilize a random prior or a normally distributed prior that would in some way resemble the training set or the true data that you're utilizing to train and then evaluate the model. The prior is a very important selection point of working with Gaussian processes or any Bayesian technique. The other hyperparameters like learning rate, etc., those can be automatically tuned utilizing tools like RayTune, etc. But choosing a good prior is utmost importance.
Okay, thanks.
Are there any other questions from the audience? If not, thank you. And Yang, I'll reach out to you directly with the GitHub repo. Let me just see if maybe I can find it real quick here, and I'll put it in the chat. This is the GitHub repo where we have all of the previous seminar slides and the associated Python notebooks. Feel free to grab them from here. There's also YouTube recordings of these sessions, so I'll share those. Let me just find it real quick and I'll just share it here. This is where we post all of our videos as well. So if you want to see previous recordings, feel free to check them out. But if there's no other questions from the audience, we'll close this session. Thank you, everybody, and I hope you have a great day.